So what we have is a video on this concept of graphing equations like x plus y equals 1. And I started class today by having you just sort of list some different ways to add up to 1 for x and y. And someone said 0.25 comma 75 is 1. Nate, you said -2 plus 3 makes 1. I had a 0.2 and a 0.8 makes 1. But then we settled on these two that are kind of important. And one would be 0 plus 1 makes 1, and 1 plus 0 makes 1. What we just found were the two intercepts of this line. And this method of graphing is known as the two-intercept method. It's also known as the cover-up method, and I'll show you why in a minute. So we had x plus y equals 1, and we realized that if you put in 0 for x, what would y have to be to make 1? And if you put in 0 for y, what would x have to be to make 1? 1. These are the 2 points that you can then plot on the graph. Not all those little ones like 0.2 and 0.8, and 0.25 and 0.75, or even -2 and 3. Those can be guide points. But these are the 2 most important points that you graph in this method. So you go to 1 comma 0 and put a dot, and 0 comma 1 and put a dot, and you have yourself a line. Because to make a line with a ruler to connect the dots, what's the minimum number of dots you need? 2. Yep, 2 is the minimum number that you need. If I took a straight edge and I ran it through these 2 dots, could I make a line? Yes, and there it is. Okay? So that's how you graph with what's called the two-intercept method. You don't need the slope. You don't need a random point on the line. What do you need? Hint, it's called the two-intercept method. You need the 2 intercepts, the x and the y. And then you have a line. So it's also known as the cover-up method because it could involve covering up x or y. Here's what I mean by that. Let's rewrite it again over here. X plus y equals 1. The two-intercept method really involves substituting 0 for x and finding y. But when you substitute 0 for x, you're doing what's called covering up x. So let's use a little box here that has some fill to it. And if I plug 0 in for x, it's kind of like covering up the x and hiding it, right? I usually just hide it with my hand, but the viewers at home wouldn't be able to see that, right? So I hit it with that box. That box is hiding the x. And when you cover up the x, what does this statement now say? It says y equals 1. So when you put in 0 for x, y equals 1. On the flip side, what does this statement say when you cover up y? When y is 0, x equals 1. All right? So that's why it's called the cover-up method in some circles of math teachers. Let's look at the next one. 2x minus 2y equals 1. Let's go ahead and write that down. 2x minus 2y equals 1. Let's graph this. And maybe about a day ago, as recent as a day ago, you might have graphed this by trying to get y by itself. Right? You take the 2x over to the right, you divide everything by -2, and that can get messy. You don't have to do that. Instead, you can use the two-intercept method, also known as the cover-up method. And here's how it works. I'm going to take this box. You can take your finger, you can take your pencil, you can do whatever you want, and you want to cover up the whole x term. Didn't mean to do that. You want to cover up the entire x term, so block it out. Let's send that little number to the back. So let's see. Okay. So you cover up the x term. And when you do that, you have an equation. And that equation says negative 2y equals 1. If I asked you to solve for that, what would y equal? If I said, get y by itself in this spotlight, what would you do to both sides?
Divide by negative 2.
You would divide by negative 2. Go ahead. What would y equal?
0.5.
Negative 1/2 or negative 2/5. So that means the first intercept is 0, negative 1/2. When you plug the 0 in and cover up x, you get negative 1/2 for y. So we have a point we can plot. 0, negative 1/2 is one intercept. How many do we need? 2. It's called the 2-intercept method.
I like 3.
But there aren't 3 intercepts unless you're graphing on the 3D plane, x, y, and z. And that comes later in your mathematical career. So for now, we only have x and y. It's just a 2-dimensional plane, right? Length and width. But the next part of the process, by the way, so we just basically put in 0, and we got negative 1/2, and we plotted it. Let's put in 0 for y now. As I said, now we're finding the x-intercept by covering up the y term. And again, we get a high y. All right. And when you cover up that term, what do you get for x? When you cover up the entire y, you divide both sides by 2, what do you get? The 2x equals 1. So what would x be? 0.5 or 1/2. So the y-intercept is 0, negative 1/2, and the x-intercept is 1/2, 0. So those points are very close together, aren't they? Dangerously close together. So we have the 2 intercepts, but they're good enough. 2 points are good enough to create a line. So I'm going to now join those 2 points together and hopefully continue the pattern that you see. And there's your line. And look where they cross. If you can't see where they cross, let's zoom in a little bit on where they actually cross. All right? Where were they supposed to cross, according to our solution from yesterday? 3/4, 1/4, right? And this is about 3/4 of a unit to the right and 1/4 of a unit up. And that's where their intersection is. So that's graphing using the 2-intercept method. Go ahead and try it for example B. Let's try it for B. Pause the video and then check your work. So we're going to go ahead and continue. We got to this point in example B and we paused and we thought that maybe this would be worthy of the video because when you cover up the y, you can see in blue, by the way, we have in blue the x and y intercept of the top equation. But in green, when we cover up the y and divide both sides by negative 2, you get what? You get x equals 0. So in other words, when you put 0 in for y, what do you get for x? 0. Well, what do you think you're going to get when you put 0 in for x? 0. So how many intercepts does this graph have? 0. 1. It only has one intercept, and that intercept is.
Let's test it. Just scream into it.
Oh no, it's from here. Delete. Okay, here we go. So we now have the both intercepts are in the same place. So now we only have 1 point. Is that enough to make a line? No. What should we do? We need to find an alternate point. This is a rare case where it actually goes through the intersection. Or you either need to find another point that'll work, like 3, 2. Right? Won't 3, 2 work? What's negative 2? What's negative 2 times 3? Everybody, what's negative 2 times 3? That's right, negative 6. Good. Okay. What's 3 times 2? 6. And what's negative 6 plus 6?
0.
All right. So that's a point that will work. 3, 2. Here's another way to do it. Anybody know what I did to get from here to here? You should. As high school sophomores, freshmen, you should know that I added what to both sides? 2x. Okay, I added 2x to both sides. 0 plus 2x is 2x. Okay. Now, what would you do to get y by itself? You should know what you do next to get y by itself. Divide by 3. And when you do, you get 2/3 x. What's the slope of that equation? 2/3. So from here, go up 2 over 3. Dot. Up 2 over 3. Dot. So that's sort of the moral of that story is that sometimes you have to shift gears because the 2-intercept method will fail if you only have 1 intercept. By the way, when I went up 2 over 3, where did I land? What point? That point right there is what, comma what? 3, 2. What point did I tell you was another point on the line? Remember? Sorry. Now we can see on the graph that they intersect somewhere. Where do they intersect? Do they with what we did yesterday? Okay. On this graph, where does it look like they cross? 3, 2. But do they? Go back and look at our answers from yesterday. Where do they meet? 3.6, 2.4. It wasn't exactly 3, 2. So that's another instance where you do one method and you think you have their intersection, but you do another method and you confirm that it's actually a little bit different. So what we're getting at here is, should we graph these? Should we always use substitution? Should we always use elimination? Is there one method that works best every time? No. It's always a little bit different, right? You'll have the freedom, as we finish here, to choose the method that you like best for the problem that you see.